Okay. All right. Did that the remote didn't work, right? No. Okay.
So there's a mouse if you want to use it.
Oh yeah. Okay. I can do that. I can. Yeah. Maybe I can be here so everybody can see. Is that all right? Is the light going down a bit? Just for the pictures, I think. Because then it looks better that way, doesn't it?
Oh,
yeah. Okay, I will put the mouse up here. Okay. All right. So thanks very much for having me. I hope I can tell you something interesting and exciting about what I've been doing the last couple of years. I've been working on a number of different projects. Those of you who know a little bit about me probably know that I like to spend a lot of time on a few things rather than cranking out a ton of images. So my presentation will reflect that. But first I'll show you what's... oh, is that one connected? Is it just the button? Oh, hang on. Oh, it's because it's...
maybe it's on.
No, it's fine. It's fine. I'll do arrow key, good old arrow key. Okay, so I'll just tell you a little bit about myself and my equipment to begin with. So I grew up in Denmark a long time ago. I've been interested in astronomy as long as I can remember. I moved to New Zealand more than 20 years ago to enjoy the scenery and all the friendly people and the nice climate. And the southern night skies was a nice bonus. I live out in the Eta Carina Ranges, West Auckland. So as I say, I specialize in sort of very long exposure, deep sky astrophotography. My combination of telescope and camera gives me a very narrow field of view. It's about the size of the full moon, so it's not very big on the sky. So the resolution on my camera is like less than 1 arcsec per pixel. It doesn't mean that I can necessarily reach that resolution on a deep sky exposure with guiding and all that, but it just gives you an idea that it's usually quite narrow field of view, highly zoomed in images. So my favorite targets are unusual or rarely imaged objects, or familiar objects, but maybe with a twist, presented in a new way somehow. So I like to do ultra deep images. I have taken some pictures of what's called light echoes, and I will show you a few of those. Gravitational lenses. Quite a few years ago, I took a picture of the circumstellar disk around Beta Pictoris. So unusual stuff like that, off the beaten path. I have observed and photographed the sky for decades with different instruments. So in 1990, I got my first telescope, a traditional little refractor. A couple of years later, I upgraded to a 100mm refractor on an equatorial mount. In 1995, I got a 10-inch f5 Newtonian, and I did some brief experiments with film astrophotography, but it was quite clumsy, and I never really quite got into it. Then in 2003, I started using a long exposure modified webcam. That was all the rage at the time. Everybody was modifying their little webcams. So with that, I could take some of the brightest deep sky objects, and obviously the moon and planets. In 2004, I got my first observatory, which was a traditional garden shed where I modified the roof so it could roll off. And that's the one you can see at the bottom left. A few years after that, we moved house, so I had to build another observatory. Same idea, a roll-off roof, but it was a little bit more permanent. It was sort of an outhouse with a more solid construction. And after that, I got a 12.5-inch f4 Newtonian reflector, which I built myself to make it lightweight. It's the one you can see over on the bottom right, and also in the middle picture below there. And then in 2016, we moved house again, and I had to build another observatory. And then this time I decided to get a fully automated dome. So let me show you my setup. So that's the dome, and that's the telescope there. So this is out in the Eta Carina Ranges. And the sky there pretty much illustrates what I can see. I mean, it's a DSLR image, so there are more stars in this image than you can see with the naked eye, but I can definitely see the Milky Way and the Magellanic Clouds, stuff like that. I think it's decent for a suburban, semi-suburban site in a city like Auckland. It's still reasonably dark, but I have to say over the last 20 years I have noticed the increasing light pollution in Auckland. All right. So this is the setup I've got. So I got obviously a mount. It's a Lost Mandy G11 mount. I got the thrust tube telescope there. Conical primary mirror, so it's a fairly lightweight mirror. I have the camera up there, which is currently a QSI 683, but I've just received a new camera, which is the one over there. And I just got it a week ago, so I'm currently experimenting, but it has a slightly bigger sensor, and it's a CMOS instead of a CCD. It's more sensitive, it has smaller pixels, so let's see how that plays out. But so far I'm very happy with it. I have a moonlight focuser, I have a bit of dew control on this, and it's all running on a little computer that's on the pier there at the bottom. And then the dome is a scope dome, 3M, which means it's a 3-meter diameter. So it's a decent size. You can easily walk around the telescope in there. And then it's all controlled remotely, so I tend to sit in the house and remote control the PC. So that's my setup. All right. So as you all probably know, astrophotography is a journey. So more than 20 years ago, when I came to New Zealand, I cracked out my little webcam and got this picture of Cantaurus A, because we can't see this from Denmark. And I was very happy and excited with this picture on the upper left. And yeah, as you can see today, it looks very grainy, very noisy. The integration time is like a couple of minutes, so it's pretty pathetic by today's standards. Some years later, I used a proper CCD and got the next image up there, which was a lot better. But you can see the stars are still blown out. They're all white, overexposed. In 2013, I took my first really deep image, so over 100 hours, and you can see a lot more detail in the galaxy now. And since then, I've taken more and better images of it, which I will show you. All right. So for this purpose, you want to get as much data as possible. I don't think you can ever have enough data, if you ask me. Obviously, there are diminishing returns, but it's also fun to gather obscene amounts of data and see what you can do with it. Yeah. All right, but to do that, you got to plan your imaging sessions, because if you're going for a really long exposure, like 100 hours, this is going to take like an entire season, where your target will obviously change its location in the sky with the season. So you got to consider a few things. You got to consider how your target is going to be positioned over the year. You're going to consider that the moon phases are going to change many times over this project. Obviously, the weather will change. If you want to get the most out of it, you should calculate your optimal exposure time, sub-exposure time, and there are tools online and in programs like PixInsight to do that. And then another thing, the seeing is going to be variable. So if you do monochrome LRGB imaging, you probably want to take the luminance when you notice the seeing is really good, because that's where the detail in the image comes from. And then when the moon is up, you can still actually gather data, right? You can obviously do a narrow band. So if your target includes some H-alpha or O3 features, you can keep going on that. You can even do near infrared, red or even green, maybe not a full moon, but if it's like half moon or something, I found that that's still reasonably okay. You don't lose that much sensitivity from that. And in the worst case, switch to some other bright targets. You can still be out imaging, so go for some globular clusters or open clusters. They usually look good no matter whether the moon is up or not. The pictures here just show sort of my an attempt at organizing my data. So it's some spreadsheets with the nights that I've been observing, how many images I took in each filter, and you can see on the left bottom here, this is the this is Maxim DL, so that's an image acquisition software. So the data is coming in. You can see Cantaurus A there. This is one subframe. You can see the guiding graph is going there. And at the bottom right, it's just a graph of how my exposure time has accumulated over time. This is for another project. It's not Cantaurus A, but it illustrates the same point. So you can see that I actually took a lot of red, green, and blue in the beginning, the bars there, and not so much luminance. So I suspect, this is years ago, but I suspect that the seeing was probably not good. So I did some RGB imaging instead. And then at some point the seeing got good. I took a lot of luminance. It suddenly bumps up and the RGB doesn't really change. And then I basically worked on the luminance for quite a while and a bit of RGB in between. So just to show that it's a long-term thing and it adds up over time. All right. So this is just to illustrate the signal-to-noise improvement you get from increasing exposure time, and as astrophotographers, you'll probably be well aware of this. This example is from another ultra deep image I did of the Antlia galaxy cluster, 152 hours back in actually 10 years ago. That's scary. The images here, there's no processing, it's just default stretch in PixInsight, but it just shows a single frame of 5 minutes up to the upper left, and then pretty much doubling the exposure time for every frame, more or less. So it goes to 1 hour, well that's not a double, but that's like the first stack, and then 3 hours, 6 hours, 12, 30, 58 hours, 103 hours. So you can see how the noise disappears over time. And to the right, you can see the final crop from the main image of that piece of sky in color. So you can obviously argue, is it worth going from the 50-something hours to the 103 hours? I don't know, but it was fun, you know. And yeah. So, but evidently, you know, the more data you have, the more you can get out of it, the more detail you can see.
Rolf,
yeah.
A question about that image. The sort of linear streak at the bottom, going past the red star. Do you know what that is, or what's causing that? It doesn't look like a diffraction spike.
I think it is a diffraction spike from a star that's just out of the. I think it's just out of the frame there. Yeah. So I think the next slide is the actual image. Yeah. So it's this one. It's this one here, right? So we were just seeing that a little bit. So that's the whole image. So this was just a little zoomed in area so you could see the noise. So that's the Antlia galaxy cluster. For some reason it's not imaged very often, or at least it wasn't at the time. But I thought it was a very pretty and interesting deep field. Yeah, and with there's a supernova remnant called the Antlia supernova remnant. Which is, I think it's like many degrees extending across the sky, and this is just a tiny fraction of it, but it happens to sort of stretch across the cluster, so it gives a nice twist to the image.
Does the cluster have a Higson number?
It has an Abel number, I think, but I can't remember off the top of my head what it is.
I'll look it up.
Yeah. So.
Exposure for 152 hours, since we know the star is moving.
Yeah, so the telescope will lock onto a star and keep guiding on that and keep following that. And then I keep taking like 5-minute sub-exposures, for example, 5 minutes at a time, and I save all those. So I can keep doing this over many, many days or months. And then I can add all the data together, and then the 152 hours is the grand total of all the images, right?
So it's a compression of the data in terms of
Yeah, it's like you stack it all together and then you can reject. So if you have satellite trails in some of your frames, stuff like that, it gets rejected. So they are like statistical outliers in the data. So you get a clean image when you put many images of the same object together.
I presume PixInsight does this, but do you have software that it works out the sharpness of the image by looking at the roundness and the tightness of the stars?
Yeah, you can do that kind of analysis in I think most image processing tools, and definitely in PixInsight. Yeah, so you can analyze that. You can analyze that in Maxim as well. You can see like the full width, half maximum, stuff like that for your stars. Yeah.
It cleans it all up so you get a clear image, basically, right?
Yeah. So you put all your sub images together. If you have a lot, that can take a while because it got to calculate the average of all your pixels in this stack of images. But then you get something like that. Obviously, if it's a monochrome camera, you don't get a color image just like that. You've got to do that for each channel. So luminance, red, green, blue, and then you can put them together in a color image, right? So I will typically do that kind of work in PixInsight, but then after that, I do take it into Photoshop and do a few more tweaks and maybe repair a few things if there's some hot pixels remaining or whatever. I like to sort of go through it and just meticulously make sure that it's all good. All right. Okay, so the main topic, Cantaurus A. I'm sure you all know or have seen a picture of this galaxy. It's what's called a peculiar galaxy. It's about 11 million light years away, and it's in the constellation of Centaurus. Centaurus A actually refers to the central black hole, the radio source, and the catalog number of the galaxy is NGC 5128. But I think everybody calls it Centaurus A, meaning the galaxy. It was discovered by James Dunlop in 1826, and I believe he used a 9-inch telescope. It's the closest active galaxy to us, and active means that it has a central supermassive black hole, and is one of the most studied galaxies in the whole sky. It's also one of the strongest radio sources in the sky, and in radio it has these giant lobes coming out on each side. So this is like several degrees wide, so that would look very impressive in the night sky if we could see radio wavelengths. It has these magnetic fields in the disk around the supermassive black hole, and they cause jets to emerge from the north and south pole of the black hole. And these jets shoot out, and that's what you can see in the X-ray and the other radio, the red one and the blue one there. You can see the jets shooting out of the galaxy. And this can be detected on Earth as radio waves, but there's also an optical part to this. So in hydrogen alpha and oxygen 3, you can actually see this radiation. So that means that with normal astronomy cameras, we can actually pick this up and see the jets, which is very exciting. On the top right, there's an image that's sort of heavily processed. This is from a study quite a few years ago, where they sought to sort of emphasize these little shells that the galaxy has. So it almost looks like an onion, and this is because galaxy collisions produce these shells when the stars get ejected into highly eccentric orbits, and you get these shells every time the cores of the merging galaxies come close to each other. And I have a video that shows how that looks like. And then at the bottom right, there's a picture, a close-up of the dust lane from the Hubble Space Telescope. And this is just a small version of it. If you find that one online, it's really impressive. You can see every single star in Cantaurus A. It's amazing. Okay, so this is the video. So I made a simulation quite a few years ago that just shows these two test galaxies colliding, and it just shows the evolution over time and how these shells evolve, and then it'll fade to an image of an actual galaxy where you see the same phenomena. So just to illustrate what's going on there.
Yeah, that thing broke.
Okay. This is upside down, north-south. So the jet you see going down to the 4 o'clock position is the northern jet, all right? And south is then to the up. We don't see the southern jet because it's pointing away from us. So because of what's called relativistic beaming, its light will not come to us. Where on the other hand, the part of the jet that's pointing towards us, we can actually see the optical light from it. However, in radio, you will see both jets, all right? Now, in this image, later on, I actually discovered that I had done the first optical detection of the southern jet. So that was exciting as well, and I'll show you a slide with that. So this also sort of shows the complete halo structure of Cantaurus A with these shells. And all the stars in front here are actually not stars. 709 of them are globular clusters of Cantaurus A. So if you look up catalogs, you can figure out which of these dots are actually what. And it's fascinating that in this little field of view, there's more than 700 globular clusters, when our Milky Way only has around 170, I think. So Cantaurus A is like a big beast. Yeah. All right. So this is an update from 2018. So now you can see the jet coming down a lot more clear. You can see the red and you can see some blue stars next to it. You can see more hydrogen alpha in the dust lane in the middle. So I added 10 hours of narrowband and my processing skills had improved, so I processed it again. So overall, I got a clear view, a bit more contrast of all the different features of the galaxy. So overall, this was 130 hours at this stage. All right, and then just to show you the southern jet that I talked about. I noticed that there was a little red blob. It's next to the red arrow there. And in the insert is my image. There's a little red blob there. And this is not hydrogen alpha. This is more like red and infrared radiation. I was speculating that this was probably part of the southern jet that had not been imaged before, because it was not catalogued as anything, and it's sort of in the right position, directly opposite where we see the other part of the jet. So I wrote on my website that there's a faint trace of nebulosity, is likely related to the southern jet, but that's about it. I could not prove that this was in fact the jet. Then a couple of years later, a study comes along, and they reached out to me and said that they had actually seen this in my image, and they put a footnote in the paper saying that that was actually the first detection. So that was nice of them. So yeah, so when you gather a lot of data, you might find something new.
Sorry, I'm so new.
Yeah.
Yeah.
Yeah. So there's a supermassive black hole in the center of the galaxy, and it shoots out jets from its poles in opposite directions. So when we look at the image, I'll go back to the image. So when we look at the image, so the black hole will be in the center in here, the bright part, and this part out here is the jet. But the image is upside down compared to normal compass directions. So this is actually north, and up there is south. So this is the northern jet from the black hole, which is visible, and many pictures have been taken of that. But there's also a southern jet that we can't see. All right, but in my image, there's a tiny red dot up there somewhere, which is actually the equivalent of this here. So there's another jet going the other way. And in radio waves, they can easily see both, but in optical, we can only see the one that sort of, this one is pointing a bit towards us, and the other one is pointing away from us. Yeah.
So, Rolf, is it known what the jet comprises? Is it radiation? Is it Hawking radiation or something like that? Or
It's
material that's ejected that's not consumed by the black hole?
Yeah, I mean it's the radiation from the black hole that comes out and likely hits interstellar clouds of gas.
It's exciting.
You know, so it's so this red radiation here is hydrogen alpha, for example. Yeah. So that's because it's exciting the gas that happens to be there, right? All right. All right. Okay, so after I did this image, I had a few people suggesting to me that I should do a mosaic. It should be even bigger because my field of view is not that large. It doesn't even cover the entire galaxy here. It's actually larger than that. And I was thinking, that's crazy. That's going to take forever, you know. But it could be fun, right? So someday when you don't have anything to do, you start a 100-hour mosaic. So that comes here. Okay, so then I started gathering more data, and you can see up to the upper left here, you can see the mosaic tiles, just checking that they actually overlap a bit. This is just lining it up. This is not the actual image, right? So you can see the vignetting and all that, but that would be the field of view, right? So from February to September 2024, I gathered more data on this, on the 4 panels, and I obviously had the center panel already, 130 hours. So all up, I was able to get 321 hours in total, including 126 hours of narrowband. I only had 10 hours of narrowband at that point, so this is a lot more. So you can kind of see the point here, because on the bottom left, this is a single hydrogen alpha subframe of 5 minutes. So Cantaurus A is just up here, and if you recall what the jet looked like, there was a little inner one, and there was some outer stuff. It probably doesn't really show on the projector, but in the raw 5-minute frame, you can faintly see a trace of this stuff. On the other side, you have the final 73 hours of hydrogen alpha, and then with the stars removed. And you can suddenly see that this jet is actually like a continuous object with a very interesting structure. It almost looks like sprites coming out of the galaxy. And I don't think anybody has seen that stuff before. And it extends a lot further than what I've seen before. So I'll show you the final image. So that's the final image. So now the field of view is a lot bigger. You can see that the galaxy actually extends along a north-south axis, and you can see the jet clearly coming out. You can see the southern jet. You can see the red spot. It's a bit clearer now, and obviously the dust lane and a lot more detail and contrast. So I'll just talk to a few things that you can see in here. And this is the sort of traditional version with stars as you would normally see it. What I then did was I wanted to remove all the foreground stars and only see what's the true background. So Cantaurus A and all the distant galaxies behind it. And I'm going to talk about how I did that. So here's the starless version. So you can see it's still full of dots, but all these dots are galaxies or globular clusters. There's not a single foreground star left. So yeah, this is basically what I just said. So yeah, lots of new detail in the jet, and also you can see there's blue in the jet. So I collected a lot of oxygen narrowband as well, and you can see there's I think I have an annotated image of this there. So there's a blue arc in here, this one. So that's like a stream of a dwarf galaxy that got too close to Cantaurus A and got ripped apart. And it's approximately 300 million years ago that happened. So it's still hanging there, the stream. There's the central dust lane, obviously. There are all these shells that we just saw in the simulation, how they form. There are a lot of dust patches, not just the central dust lane, but little patches everywhere across. And you can see that massive halo sort of extending out in as a line almost. And then you have the jet there, and then everything in the background is either a distant galaxy or a globular cluster. So in this field of view, there's more than 1,100 globular clusters of Cantaurus A.
Well, how big is that?
The jet.
Well, the whole galaxy.
Yeah, the whole galaxy. I think the jet is probably 100,000 light years from memory, something like that. So maybe it's 200,000 across. Yeah, yeah, something like that. But I mean, this is the faint extension. So I imagine the Milky Way also has faint extensions that we just maybe don't know about. So if you compare to the Milky Way, maybe it's only really the inner part that we can compare with. Maybe they're similar size, but they both have a large halo, something like that.
Rolf, do we know anything about the supermassive black hole and its mass?
I am sure we do, but I can't remember off the top of my head the mass. But it's not one of these billion solar mass black holes. It's in the millions. Yeah. I don't know if anybody else knows. No? Okay. Okay. Thank you. Okay, so a close up. So you can see the dust lane, the dark dust patches everywhere. You can see this blue arc, the sad remains of an unlucky galaxy. And then you can see the jet, the beginning of the jet there, and you can see lots of features. To me, it almost looks like these sort of sprites that come out of thunderclouds that people have started taking pictures of, right? It looks a little bit like that. So there's a lot of new detail there that I haven't seen anywhere else. And you can see that the jet, the inner part and the outer part are clearly connected in one long stream. And then you have sort of the overlay with the shells of Cantaurus A. So it looks quite pretty, I think.
So Rolf, is the plane of the galaxy on a tilt to the screen?
This is an elliptical galaxy, so it doesn't really have a plane. The dust lane is believed to be the remains of yet another galaxy, maybe a spiral that came too close not too long ago. And it's dust and gas is just hanging there and happens to just pass right over the center from our point of view. So, but the galaxy itself is really a large elliptical galaxy that's grown by merging with other galaxies over billions of years. So it doesn't have a sort of a plane as we do in our Milky Way.
Those two jets are that one's coming towards us, the other one's going away.
Yeah.
So there's a tilt to that axis, if you like.
Yes, so that would be maybe the axis that we could talk about. So yeah, this jet that you can clearly see is leaning towards us, and the other one is going a bit away. I don't know if I don't think that the Milky Way central black hole is lined up with its axis either. I imagine it's pointing another way probably. Just like the solar system is pretty random, right? It's not lined up with the Milky Way either. So
Still sorting itself out.
yeah, yeah.
So you wouldn't expect it to be rotating in the plane of the majority of the stars? Like, I mean, for us as a plane of the galaxy.
I don't know. I don't know whether it does. I mean, the solar system just seems to be random, right? The black hole is obviously much heavier, but I don't know whether they really align up with the plane of the galaxies as such. I don't know. Interesting question, actually. Yeah. Okay, so more jet. I think I have talked to most of this, but here this is just another crop of the image, just to sort of illustrate it. So you got the massive black hole in the middle in the bright core. We can't see it obviously, but that's where it is. And then you got the jets shooting out in both directions, right? So the familiar colorful big jet there, and then the little red blob, and you can see that they sort of line up across the middle. So this is sort of the full extent of the jet, I believe. It does sort of continue maybe a bit out of the frame still. And that was, as I said, 126 hours of narrowband. I have since collected another 100 hours of narrowband on this, so almost doubling it. So I haven't stacked it up, so I don't know what it'll look like, but I'm sure there'll be more detail in there. So looking forward to that.
Ralph, in terms of size and number of stars, how does that relate to our own Milky Way?
Yeah, so the size, I think the size of sort of the main shells there is maybe comparable to the Milky Way, but because it's an elliptical galaxy, it has a lot more stars, because it's like a ball. Yeah. It's not flat like our Milky Way. I don't know exactly the number of stars, right, but I imagine it must be a lot more than our Milky Way, right, because it's like a spherical volume.
It's been subject to a lot more interference from.
Yeah. So it has merged with many galaxies over the years, right? And at the moment we can see this one, and this is believed to be the remains of another one that just happens to be right across the core.
Just a comment, Rolf. I can still see it in my 8-inch scope at home. You can't see it in the 20-inch scope here.
Oh wow.
Just because of the Auckland light pollution. When I first joined, you could see it from here.
Oh yeah.
You can't see it anymore.
Wow. Yeah, that's fascinating.
Not enough contrast with the light pollution of the city.
Well, that's fascinating, isn't it? All right.
The structure in the jets, that's just because of whatever gas clouds are in the way of the.
Yeah. So the jet there, yeah. So I mean, the jet is obviously not a straight line, right? But I think that this is probably due to maybe precession of the black hole over time. So the jet has pointed different ways. So it's almost like a hose, and the water comes out, and you can see that it's.
It does kind of look twisty.
Yeah, right. Yeah, it's almost like it's sort of spiraling around, maybe. Don't know, but it seems to have changed direction, right?
It's interfered with, isn't it, by other matter?
Yeah. So yeah, it seems to currently point maybe up there, right? Where in the past it has been pointing in another direction, and it probably changes a bit over time, just as the Earth's axis is changing over 27,000 years or whatever, right? So over millions and billions of years, this black hole is probably changing its rotation plane. All right. Okay, so this is just to show that when you separate the foreground stars from the background stars, and you have the narrow band by itself, you can start playing with things. So on the top left, you have everything combined, and then the foreground stars, if you then subtract those, you get just Cantaurus A and beyond, right? So the Cantaurus A system with its globular clusters, and whatever background objects there might be out in the distance. And then you can do further subtractions of these things and get just the extragalactic sources. I have another image that shows Cantaurus A, like the Cantaurus A system. So just the galaxy and the globulars, but no background galaxies or foreground stars. And you can take the globulars away and the narrowband away and just see the structure with the shells. These are just small crops of the main image, right? And then you have the traditional H-alpha O3 narrowband that you can combine as you wish. So once you have all these different layers, you can do a lot of interesting things. So I'll just talk about how I've been doing that. And this is the Cantaurus A system only. So Cantaurus A and globulars. There's nothing else in this image. So every dot is a globular cluster. And you can see how they sort of congregate towards the center, as you would expect. All right, so removing the foreground stars. And Bill mentioned the Hubble Ultra Deep Field. So I'm going to talk about that one as well. Okay, so so this is another project I did in the last couple of years. So trying to take an image of what's called the cosmic web. So the cosmic web is this large-scale structure that you typically see in computer simulations or like surveys of billions of galaxies. You can see that these sort of foam-like, web-like structures show up as a three-dimensional structure. But I had never seen an actual picture of this stuff. It's always computer simulations or 3D reconstructions. So I was thinking, what if I take a really deep image of like an empty point in space, like the Hubble Deep Field, and remove all the foreground galaxies? Will I see the cosmic web show up? So that was the attempt here. And as you probably know, the cosmic web, its origin is sort of these tiny fluctuations in the dark matter that happened immediately after the Big Bang. So they were sort of imprinted on this cosmic microwave background that we got from the Planck satellite. And over the lifetime of the universe, these structures grew and became these hundreds of millions of light years wide voids today. So it's sort of this soap bubble structure on a very large scale. Okay, so I took an image that I called the Fornax Ultra Deep Field, and this is an empty-looking field. It's about the size of the full moon. The good thing about this area of the sky is there's almost no obscuring dust or nebulosity, no emission nebula. So it's almost like a window out to the distant universe, because pretty much everywhere you look, there will actually be something in the foreground, usually stuff that we want to take pictures of. But if you want to see what happens billions of light years away, you want to find some kind of hole between it. So this is also the location of the actual Hubble Deep Field. That's why they chose that spot. So I thought, I'll try and take a deep field of that and see what it looks like. So this is a 60-hour exposure with around magnitude 75 limiting magnitude. So this is just from my planetarium software. It's the little red square in the middle, and that's the field of view of my camera. So these lines here are various Hubble telescope studies that have been done over the years. So the red is the Hubble Ultra Deep Field, the south one, because there's a north one as well. The turquoise is the Extreme Deep Field, which I believe was one where they added infrared data some years later. And then there's the yellow one and the white one, some other studies. This is a very, very studied area by the Hubble telescope. And as I said, the image in the background is then my version of this field. Now, to work with that, I wanted to remove the foreground stars. So you can do that. Obviously, these days you can do that with like AI tools, Star Exterminator and things like that, plugins to various image processing software. But the problem with those is that they will remove every point source in your image, regardless of whether it's a distant galaxy or a quasar or a globular cluster or an actual star. The software doesn't know what it actually is. It just recognizes a point source and it will remove it. And it's very good at removing it. You get a really nice, smooth, starless image. But the problem is that if you want to look at the true background, you're going to lose that if you make it starless. So what I did was I looked up catalogs online, which you can look up for free in multiple places. So you can find, for example, the Gaia data, which has every single star that we know of, pretty much. So you can download all the Gaia sources that are within your field of view, and then you can take it into something like Excel, or you could use Python or whatever you want to do, and you can filter it. So all the Gaia sources have an assigned probability of like being a quasar or being a galaxy or being a star and so on. And what I did was I basically just filtered that, and I said something like, if it's 80% probability of being a galaxy, then I'll keep it, something like that. You got to decide for yourself what you want to do. So I filtered this in Excel, and I ended up with basically a catalog of all the true background sources. So anything except the foreground stars. So removing the things that are truly foreground stars, right? Then in, for example, software like PixInsight, you can import this custom catalog and then overlay it on your image, and that's what you see down there. So all the little crosses are now the background, the foreground stars, so the correctly identified foreground stars. And you can see that most of the objects in the image are actually background sources. There are not that many foreground stars. If I had done automatic starless on this one, it would have just been a flat field with maybe the big galaxies remaining. That's it. So you have to manually do this, and it's quite a bit of work to do this still. Now I then saved this as an annotated version of my image for later use, and I'll show you how. So the next step, as you can see up there, you have the original image. Then I did the actual starless process, so remove every point source in the image. So then I get sort of the background up there, and I get the AI generated star mask. So that's an image that only contains the stars, but nothing else, only the point sources. And then in a tool like Photoshop, for example, or whatever you prefer to work in, you can then hold that star mask up against your image that was annotated with the Gaia sources, right? And then you have to manually remove all the point sources from your star mask that are not foreground stars, and that takes a while. I mean, you can do some selection, and you can do some of it a little bit using the inbuilt tools, but I have to say that there's quite a lot of manual cleanup work, and obviously you have large stars and spikes and stuff, so you've got to use a bit of common sense to get it right. But in the end, I was then able to create this final star mask. So this is the image from before, but excluding all the background, right? So it's completely pitch black, except for everything that is a foreground star. All right. So what's left to do is really just to take the original image, apply the star mask, so basically remove all the stars, and then you are left with the background, and that's the one down there. And then, as I mentioned before, then you have these two layers. You know, you can start playing with that. You can make animations out of it or whatever, and I'll show you an example of that. And I have a link to that there, and I will play that video in a little while. So just to show you, this was the original image, and the Hubble Ultra Deep Field is a little tiny patch in the center of this field of view. And then without the stars, it looks like this. And then that's the fascinating part, right? Every single dot of light here is actually a background galaxy or a quasar somewhere. And there's around 20,000 of these, just in a little field the size of the full moon. And I think you can sort of see that these galaxies are not randomly distributed. It doesn't look like random noise. There are clearly structures, lines, and clumps and so on in this. So I think we are sort of looking at the cosmic web, an actual image of the cosmic web, right? It's just that the foreground stars kind of obscures this view. It's hard to separate the stars from the background. And it's pretty much the same thing as when people remove the stars from a nice nebula image, right? You can better appreciate the nebula when you don't have all the irritating foreground stars.
Rolf, if I may, it looks like material in a medium, doesn't it?
Yeah.
You know what I mean?
Yes, yes.
It's hanging together.
Yeah. It is sort of these long threads. So let me just see. I think the next one is the video. So I will just show this video I put together. So you can see what it actually looks like. I go away so you. I know I can see that one. It's pretty fun to put stuff like that together when you have the different layers. Someone else asked me whether this actually was reflective of the true distances to each individual star, and I had to say no, I didn't go to that length. But I am working on a similar video for Cantaurus A, and I have actually organized the stars into proper distance. So, all right. So as I said, this was also the location of the Hubble Ultra Deep Field. So on the left you have a tiny section of the main image I showed you before, and then on the right you have the actual Hubble Ultra Deep Field, which is sort of the diamond-shaped black area in the middle there. I don't know if you can see that. So you can see that there are actually quite a few of these points that show up in the Hubble Ultra Deep Field. I wasn't sure what to expect, whether I could see a couple of these things or nothing at all. But there's actually a surprising number, like around 190 galaxies that are visible in both of those areas. So they are around magnitude 20 to 25. And the furthest are up to 12 billion light years away, the ones that I can see there. So if you extrapolate this little patch to the entire field of view of my image, that would be like 23,500 galaxies at this depth. That's a lot. And in the entire sky, it will be 2.6 billion at that depth, right? So it sort of says with an amateur telescope of average size, you can see a couple of billion galaxies with photography. That's a lot of targets. Yeah.
So you're expecting an increase in the value of real estate up your way soon.
Yeah. Yeah. All right, and I put this one together for fun. So again, the Hubble Deep Field is on the right. This looks better in a high resolution image on your monitor, but you can see all these little squares are the actual galaxies that I found in the deep field, and I've blown them up there, the corresponding squares, and they're all labeled, but you can find this one on my website. It was just quite fun to have a look at all the different redshifts, and some of them are actually quasars, so it was quite interesting to look at that.
So the little details on the outside from the Hubble image.
Sorry?
All the little detail ones that are taken out of the Hubble.
Yeah, these are crops from the Hubble image, the big one, you know. So this is a small version of the Hubble image, and this is from the real big one, right? So you have all these interesting shapes and colors of galaxies. And in my image, they are just like little dots, but they're still there, which is the funny thing. Yeah.
You tempted to go deeper than 60 hours on that one?
I wanted to sort of see the cosmic rip, and I think I saw that. But yeah, I wouldn't mind taking some more data. Maybe with my new camera, I might go back and visit. Yeah. Yeah.
What with your luminance frames, have you ever done a comparison between them over time to pick up any supernova on these really distant galaxies? The supernova should probably be as bright as the galaxy. So
Yeah. You mean in just an image like this over time, you should see changes. Yeah. I mean, it's hard because in the subframe you won't see all the galaxies though. You got to integrate it all together. But like if I went back to this and took another 60 hours or whatever next year, then I would have two data sets that I could compare. That could be interesting. So and I have done something similar to what you're mentioning. So with the light echoes, which I'm gonna talk to. So yeah. So light echoes. This is. I hope you're okay for time. This is my last topic. Okay. All right. So I wanted to see if I could take a picture of the light echo from supernova 1987A. So I've seen these pictures in the past. These were taken by professional observatories quite soon after the supernova hit in the 1980s. So these are like the light from the supernova obviously expands as a sphere, and it'll hit gas and dust and then be reflected from that, and some of that light will then go down to Earth. So we kind of see an echo similar to a sound echo, and we see these concentric rings moving out from the supernova over time. And I thought this is something you can see with like 10-meter telescopes on the top of a mountain. But I remembered I had some data on the Tarantula Nebula in the Large Magellanic Cloud. This is where the supernova happened, and that data was like 8 years old or something. And then I thought maybe I'll grab some more data and then compare and see if I can see a difference between the images, and maybe I can see this a faint hint of that. So so on the top left is a data set from 2012. It's not particularly good quality. It's quite old. It was one of my first sort of images with CCD cameras. And then in 2020, I took another set of data to then do the comparison. And then I thought, maybe there's a slight chance that I'll see something, because nobody else has done this, so it must be hard to see. And then I took the difference of the two images, so basically subtract them from each other, and anything that shows up there would then obviously be the difference between the two images, if anything had moved or become brighter or darker. And on the top right, you can see clearly these concentric rings, right? So there's a set of bright rings and there's a set of dark rings. So the dark ones are where the light was in 2012, sorry, in 2020, and the light ones are where they were in 2012, so closer to the center of the supernova, right? And this was bleedingly obvious. As soon as I did the difference image, it was just there in the stack. I didn't have to process it or anything. So that was very exciting. And here you can just see a diagram. This is the same image, right? And this is the location of the supernova, and the blue is where they were in 2012. And in 2020, they were at the yellow position.
What's the reason for two echoes at the same date? Is that different clouds of material?
So these are not actual arcs of light moving out. These are reflections from the interstellar gas and dust, and that's distributed in a random way within the Tarantula Nebula. So you will see many reflections. And close to the supernova, you will also see new reflections and so on. It just happens to look like this right now, but it's a bit random.
You can use it to get a distance.
Yes, that's right. Yeah. And I also looked at how much it had moved. So in my image, it had shifted 47 pixels. So at my image resolution, at the distance of the Large Magellanic Cloud where the supernova happened, that is the same as 28 light years, but that sounds wrong because there's only 8 years between the images, right? So how could this move 28 light years in 8 years when you cannot move faster than the speed of light? That is really just because it's an optical illusion, and I have a slide that shows how that works in the end. So this is a beta image. So I took a proper color image of the area. And then overlaid the light echo. And you can see in the middle there's a little pink dot, which is the actual remnant of supernova 1987A. There's a famous Hubble picture of that thing. It's extremely small, a couple of arc seconds across, but it shows up as a little pink dot. And then you have these concentric rings, and I think I have an image that shows the animation. So on the left, you can see the two images, and you can see how this light actually moves outward. And on the right, it's just to illustrate that it's like an expanding sphere of light that will hit random gas and dust as it expands, right?
Rolf, if I may, what effect would the expansion of the universe in that particular area have on the apparent speed?
I don't know, but probably some sort of effect. But the Magellanic Cloud is still relatively close. I think its own proper motion is much higher than the expansion rate at that distance, because it's just a satellite galaxy of the Milky Way, right? So I don't think so, but I can't say for sure off the top of my head. All right, so here's another example. So after I detected this this light echo from the supernova, I thought there must be more of these things, and it could be fun to pick them up. So then I thought about Eta Carinae, and that star is well known for having what's called the 19th century great eruption. So in the middle of the 19th century, Eta Carinae became, I think, the second brightest star in the night sky. So almost the brightness of Sirius. And today you can't see it with the naked eye, or maybe it's just maybe you're just able to see it if you're at a dark location. So that's a huge difference in magnitude. And so it had a massive eruption, and this lasted for a couple of decades. So I was thinking that there must be maybe an echo left of this. It's in the middle of the Eta Carina nebulae. There's a lot of stuff that this light could bounce off. So I searched around, and I found that the Hubble telescope and a couple of others had actually taken pictures of this light echo. So I found that, and then I extrapolated where should this echo be at this point in time, because their images were a couple of years old. So the light echo I then found was out here, and which is, if you're familiar with the Eta Carina Nebulae, this is a mosaic. So it's quite a large distance. It's like I think it says 40 arc minutes from Eta Carinae. So it's like in the other end of the nebula, basically. And I have a close-up of that. But yeah, this was done over 2 years. So I took 3 data sets over 2 years, and over that time, I could actually see this echo move quite fast across the nebula. And then same thing. This is the light echo overlaid on like a deep color narrowband image of the nebula. So this is the animation of the light echo. And on the right, I've just color coded. So on the right, the blue echo is February 22. Yellow is March 23, so like a year later. And then the last data I got was December 23, so not quite a year after, but still quite a long time after. And that's the red tips of it. And there you can see the 3 frames, and you can see how it propagates down through the nebula. So that is quite fascinating that you can see these transient things in the sky. You know, it's not static as we tend to think. This is because this is just a tiny little fraction of the light echo. There will be this will spread out in all directions, but it just happens to hit something here and then be scattered towards us. But there's also echo over here, or light passing through here, but it's just not hitting anything, so we can't see it. It doesn't get scattered to us, so it just carries on in its own direction, right? So just to explain how it works, right? So this is the example of the supernova, but it could be any bright light source, right? But for us to see it, you know, it's got to be like a supernova or an eruption like Eta Carinae had. So you can see that the light starts at the light source there, the supernova in this case, and it will go out in all directions, but it might hit some kind of gas or dust cloud at some point, right? And when it does that, that will scatter it again in all directions. Some of that light might hit the Earth, and then all the light that hits the Earth at the same time will have come from points that are on a grand ellipse with the light source and the Earth at the focal points. So that's just math. If they arrive at the same time, it will have to line up that way. So that can basically tell you something about the 3D distribution of this gas and dust in space. So as you observe these light echo over time, you can almost reconstruct a 3D map of the nebula, right? Or at least the parts of the nebula where it reflected light to us. So this is the other one. So the superluminal motion. So I made this example just to make it simple. So this is like a standard triangle, right? So 3, 4, 5 in length. So at point A, you have the supernova, and it will then erupt with light, and the light goes down to the Earth. So that's the radiation emitted at point A. And then, as I said, it's a sphere of light that goes out in all directions. Of course, the Earth just happens to be in one direction. So let's say at point B, it hits some dust cloud and it gets scattered again. And then some of that light is then also hitting the Earth. So now we see light coming from the supernova, and then later we see light coming apparently from point B in the sky, but it actually came from the supernova, right? So in this triangle, you can see that the path, the distance between the supernova to point C is 4 light years. Between the supernova and point B is 5 light years. And between point C and B is 3 light years. So it's a standard triangle, right? So the path that the light took going from A to B to Earth is really just 1 light year longer than the direct line of sight. But when we look at this from the Earth, we think that the light moved from point C to B, but it never did that, right? We just received 2 rays of light at different times. So it looks to us like it moved 3 light years in the course of 1 year. But as I said, it's really just because these 2 light paths are completely independent, and one is 1 light year longer than the other. So that's the origin of superluminal motion. And the closer the angle is, ACB, the closer the angle is, the faster this will appear to move. And we see the same thing in the relativistic jets from black holes like Cantaurus A, same phenomenon. But it is really just basic geometry. It's an optical illusion. But as I said, it can be used to calculate properties about where this takes place, right, and where the gas and dust is located. So I think that was my last slide. Yes.
Oh, thank you.
So.
Thank you.
All right.
Thank you.
All right.
We have a question before, there is tea and coffee and snacks down the end, but anyone have any questions for Rolf before we conclude?
I don't think there's any space left in my brain.
Well, I've got a question about the cosmic web image, and that comparison to the background microwave radiation.
Yeah.
It strikes me that the scale of your image compared to the cosmic background radiation is so much finer. It seems to be beyond the resolution of the cosmic background radiation. So the structure, the scale of the structure, they seem to line up.
Yeah, as you mean the picture from the Planck satellite? Yeah. So that I think was a very coarse-grained image, right? It's not very fine resolution from the satellite. It was revolutionary at the time. Yeah, it's the whole sky, right? So yeah, in my image it's just like the size of the full moon. So if you overlay the Planck image, you won't see any difference there, right? But in my image you sort of see the same structure, right? And if we had If we made a modern satellite, we might see better resolution in this data, right? Similar to what Planck saw. So it will be there, but I don't think we can see it yet. Yeah. All right.
Wonderful. Thank you. That was amazing.
I'm interested in how you end up collaborating with professional astronomers. Do they reach out to you? Do you reach out to them, or is there some sort of platform that connects?
Yeah. It has been a mix. It has mostly been them reaching out. So like when I've had an image on Astronomy Picture of the Day or something, someone has reached out, often like NASA wanting to use an image for, they used my Cantaurus A image for the launch of the Webb telescope, for example, on their website and things like that, right? But there have also been like proper collaborations with data processing. But it tends to sort of be over time, you sort of build up a network, the same people, you get in touch with them. So sometimes I reached out to people and also like scientists writing a paper. Often I'll get inspired by some paper, like the Antlia cluster, for example. I looked at scientific papers and found this cluster, and I sent them an image I sent them the image I took, right, to show them, look, this is what it looks like, the thing you've described in detail in your paper, because there were no really good images of it. So stuff like that can get you in touch with people, right, and form connections. So, but yeah, there's no real sort of formal way, I think, unless you talk about specific things like you're studying variable stars or supernovae or gravitational lensing or whatever. You know, there are sort of formal groups that you can join to do that, right? But as a whole, I think it's still a bit ad hoc, really.
A couple of the formal groups that amateurs are interested in, probably the Microfund Network, which is the Micro Lensing Follow-Up Network, which the observatory here and Jenny McCormick and the Kew Observatory were involved with that. Basically doing follow-up observations of micro-lensing detections that are picked up by survey telescopes but they can't come back to the same field with enough frequency to get the data they need, so they hand it off to amateurs. That's a specific group. And there's also if you're into variable stars, there's the AAVSO, which is the American Association of Variable Star Observers. They're always wanting amateur observations of stars. It's not the most exciting work. You're just measuring the brightness of lots of candidate stars, but it's valuable to a lot of researchers. Okay, well, thanks very much, Rolf.
You're welcome.
All
right.
An interesting amateur project that somebody put on the Astronomy in New Zealand Facebook group, and that's to see how small a parallax angle you can measure using amateur equipment. So basically measuring the distance to some of the nearby stars. Shouldn't be too difficult. Bessel did it using a 6-inch refractor and a heliometer configuration back in the 19th century, so it should be possible to measure the parallax of Cantaurus A and some of the other nearby stars.
I just get the feeling that someone's actually trying that with SLEW, because you've got the 17-inch on top of Mount Teide, and it's equivalent in Chile, which is exactly the same size, the same field of view and everything. I think he's trying to image the same thing with both those telescopes at roughly the same time.
The baseline will be too short. You have to use the orbit.
I'm not sure what he's up to. I'm not sure what he's up to, but it looks like it. Maybe he's going for asteroids.
Okay, thanks everyone.
Thank you.
Right.
Thank you.